how to write, or really remembered how to write, because I think you guys did this a bit in pre-calc, how to write kind of the summation of a series in general. And so yesterday what we did, I don't remember exactly where we finished. I think we did, I can't remember if I started at 0 or 1, but I said sigma from n equals 0 to infinity. And let's just stay right there. So if I started at 0, if I started my sigma at 0, then what would my general term be in the sigma? X to the n. Yeah, so it'd be x to the n for this particular one. And as I mentioned, and this is where you can decide to be like a massive pain in the butt, or you can just kind of be nice and easy. I had a student a long time ago that would do stuff like this, like, kind of Blake was getting at this. You could start it at like, so let's start at n equals 112, just for kicks. And if that's the case, then your nth term would be, or your general term, n minus 112. Yeah, this is somewhat simplistic. It wouldn't be that hard to decipher this, but I had a student that took great pleasure in taking some of these more complicated ones and be like, well, let's start the n here and let's make all these little modifications. And so I read through all of them, and he was really smart. He was really good. But every now and then he would mess himself up and he would do something wrong. And I'm just like, oh, if only you had just taken the easy road, like most of your friends, then it would have been good. But your choice on that. So I would go with this. You could have done this. I think this was also suggested. Try to start it at a 0 or a 1 or something, and I think it's going to be pretty good to go. So what I'm thinking is you guys should be able to handle number 2 based on that, perhaps. There might be one question that comes out of number 2, so take just a second, think that over if you have not already done so. Get your sigma going, get your general term in the sigma. We'll check it out, and if you have questions that come up, please ask, and do our best to answer. And we'll talk about all those alternating ones next.
How difficult is it to work on Doceri?
It's not hard.
Did you upload this as a document, or did you create it in the program?
So it's through this. So if you're going to use Doceri, you have to run it through your computer. Mm-hmm. So as I want to scroll and progress, I have to drop the writing panel and scroll through.
Okay.
But to me, this is the best back-end recording. The back end of the recording is super easy to produce. Mm-hmm. So that's why I use this. I think Notability and some of those other ones are really easy. Mm-hmm. Somebody else uses Explain Everything, and they really like that. I've seen it. I have not had time to really explore it.
It makes sense for this. We don't have the ability to project like this. We don't have wireless projectors. We don't have Apple TVs. We don't have any of that stuff. So in order for me to project, my laptop has to be...
Again, for the mercy of everyone, keep it simple. What'd you guys get for a sigma and an nth term?
0.
Okay, so you started at 0. That's fine. I like that. So n is equal to 0 to infinity. So if that's where we're going to start, then what would the nth term or the general term in the sigma have to be? Any ideas?
X to the n over n factorial.
Awesome. Yeah, that's exactly it. X to the n over n factorial. So if you test it out, you plug in a 0, you plug in a 1, a 2, a 3, ... You can see that it works. I think I know what Lenny's about to ask. Go ahead, Lenny.
So wouldn't the first one be divided by 0?
Ah, great question. No. We did. I think we did talk about this at one point. So the question is, what happens when you plug in a 0, that first one right there for n? You end up with 0 factorial, and the assumption is always that 0 factorial is 0. There's at least a couple of different ways to think about it. You could think about it from a probability perspective. I kind of like this one. If you think about the definition of factorial, you could say that n factorial is n times n minus 1 factorial. Is that fair to say? Makes sense? So if we agree that that's what factorial means, then we try this out like this. I would say, let's plug in a 1 right there. So 1 factorial, so all the n's are going to be 1. So it'd be 1 factorial equals 1 times 1 minus 1 factorial. And you can see the 0 show up, right? So we know that, or maybe we've agreed that 1 factorial is 1. That's obviously a 1. And then you get this 0 factorial thing right there. So you get 1 equals 1 times 0 factorial. You divide both sides by 1, and 0 factorial by definition has to be 1. You can also look at it like a probability. I guess it'd be like a combination. Like if you took 0 things. Well, think about it like this. hey Lenny, you know vectorials used for like combinations, permutations. Like if you took 0 things and tried to arrange them 0 at a time, how many would there be? Like how many different permutations would there be? One. And so you can think of it from a probability perspective too.
Like you have the Queen of Hearts, and the probability of
Or like 0 choose 0 is 1, right? So you're taking 0 things and you're choosing 0 of them. So how many ways could you do that? Once. You just don't choose anything. Okay. You guys all okay with that as far as the...
That's pretty wild right there.
You guys all okay with x to the n over n factorial sigma that Alyssa got for us? Is that good? I like it. So you're going to find out later that this can be used, if you use it as an infinite series, you can actually can equate this to this. Come on, e to the x. There we go. So we'll get into that stuff later, but don't stress about that right now. Okay, so number 3, let's do number 3 together, and then I'll kind of turn you loose on numbers 4 and 5. Did you notice how in numbers 1 and 2, all the terms were positive? They all have the same sign. In 3, 4, 5, the signs go plus, minus, or they could go minus, plus, minus, plus. So we have a name for that. It's called an alternating series because the signs alternate. And so if we were going to look at something like number 3, we could start at sigma from n equals 0 to infinity. And we start to think about, all right, what would have to be the general term in there? Let's just talk for a second about the x's. Like we can deal with the positive, negative thing separately. What do you guys think the x's would have to be? X to the n. Yeah, I totally agree. X to the n, because n, the exponent just goes essentially 0, 1, 2, 3, 4, 5. How do you think that we could incorporate that alternating element into this? Like, how could we use the sigma and the n equals 0 to infinity to make the sign go plus, minus, plus, minus, plus, minus?
Negative x.
Okay, so if you can do it that way. So if you only if you put it in parentheses, though, right?
Yeah.
So if you put it in parentheses, this would work. I got no problem with that. I am going to encourage you to think about it a little bit differently. I'll just kind of sneak this in here. I would encourage you, instead of writing it like that, I would encourage you to write it like this: negative 1 to the n times x to the n, to kind of separate the alternating element out from what's going on with the variable. I think it just allows you to see what's happening a little bit better. Because essentially at this point what you've got is you've got an alternating element that's just hanging out there going plus, minus, plus, minus, plus, minus, right? And then the x to the n is doing its own thing as well. And of course, each of the terms is just the product of those two. So what you suggested is right, but I kind of like this a little bit better. Okay, so let's see if you guys can handle numbers 4 and 5. Numbers 4 and 5 are also hopefully soon to be well-known series. Give it a shot. If you need to reference, remember we talked about the patterns for evens and odds earlier, last class, so use those as a reference if you need to. So let me hear from you guys. Sean, with number 4, your sigma, did you start at 0 or 1?
0.
Okay, so how many of you guys started at 0 for number 4? Like n equals 0 to infinity? Is that what you did? You all did? Okay. So I don't know what you did next. You could handle the alternating piece, or you could handle the other stuff. Any volunteers on maybe the other stuff? You can handle the alternating piece at the end. What do you have for x's and denominators and all that stuff? What'd you notice? What kind of a pattern?
2n.
Everything's even, therefore 2n would make sense, right? Okay. So x to the 2n. Since we're only plugging in integer values, doesn't that guarantee that it's going to be x to a positive?
Yes.
So I think that'll work for us. We can test it out here at the end. And then, did you notice all the factorials were also even? And so with that even pattern we established last time, I think we go with 2n factorial. So if you left it just like that, this would be exactly right, other than the alternating element, right? So this would just be like all positive terms, and it would match all the terms, just the plus minus would be wrong. So then how do we add in or multiply in an alternating piece?
Are you asking me?
I don't know. Whoever's got an answer. I'm standing by you, so you're welcome.
1 to the n.
Nice. And you got to use parentheses, right?
Yes, parentheses.
You have to use parentheses there. So negative 1 to the n multiplied in there. That'll guarantee that you alternate between positives and negatives. I'm always going to do a quick check at the end to make sure that I got the right ordering on the plus minus, right? So you think about the 0, -1 to the 0 would be +1. So I think it's going to work. Make sense? I would do a check, especially if you're like Blake and others that want to maybe tend to get creative with things. Make sure that that start value is actually going to get you the thing that you want. Okay, number 5. Did you guys notice that number 5 is really, honestly, it's just like number 4, except everything's odd. It's the exact same thing, except all the evens have been replaced by odds. So again, did you guys start off with n equals 0 for your sigma? You could start off at 1. It doesn't really matter. I think 0 would be kind of a standard thing. If you looked in a textbook, you'd probably see that. So Cameron, if everything is just odds, how do I get that odd pattern going on my x's and my factorials?
You could just do 2n plus 1.
Sure. So 2n plus 1, 2n plus 1 factorial. So that's going to get you all of your odds that we were looking for this one. But then like before, we got to add in that alternating element. And so -1 to the n will get us there. I've like kind of foreshadowed a lot of these in the past. Do you guys remember by any chance what number 4 and number 5 would be associated with? Sine and cosine. Which one is which?
Sine's odd.
Sine is the odd one. Cosine's the even one, yeah. So we'll come back around by the end of this and we'll like kind of prove that that's really true, but that is what we looked at in the past. Okay. Do you guys have any questions about that? That was just kind of an exercise in practicing seeing patterns. That'll come into play later on for sure. Okay. Hey, quick poll from you guys. I think I know the answer to this, but I want to make sure. You guys looked at sequences and series, right, in pre-calc, or did you just look at sequences only? Do you remember? Well, I was going to say, McKenna, let's talk about that. Does anybody know the difference between a sequence and a series? Besides that, something that's consequential.
Sequence doesn't matter what order.
Say again?
The order doesn't matter in a sequence. Or with a sequence?
Series is added up.
Well, you bring up an interesting point because with certain series, depending on how you order things, you can get like any different sum, like any sum you might actually want, which is kind of a crazy thing to think about. But with a sequence, order doesn't matter. I mean, if you want to see the pattern, it probably matters. Right? If you want to try to decipher some sort of a pattern, I would say you'd want to consider order. There's one like really distinctive difference between a sequence and a series. And it doesn't have to do with order, I don't think.
Like the arithmetic and geometric
Oh,
Oh, so there's an arithmetic sequence, there's a geometric sequence, there's others.
it's A instead of X.
No.
Don't you like add up?
There it is. Oh, you guys are not listening because you're just talking. What is it?
You add up the series.
Series is a sum of all the terms, right? And a sequence is essentially just a listing of all the terms, right? Okay. So an example of a sequence, and I didn't give you a start value here, but if we were going to give a sequence, it says list the first 4 terms in the sequence. Let's say we started for, I don't know, n is equal to 0. So I'll just put in here for n equals 0. So if we're just going to list out a sequence, we started at 0. What would be the first term in this particular sequence? It'd be 0, right? 0 over 1. Let's just run these through real quick. You guys are good at mental math. Okay, so we're supposed to do the first 4 terms. So what if we used n equals 1? That'd be the second term, right? What would that give us? If n equals 1, then the next term would be -1, right? So 1 over 1 minus 2. And then the next n would be 2. What's the term there?
-2/3.
-2/3, you're right. And then the last one would be when n equals 3. Negative what? -3/5, okay. Agreed. You know what? Let's make it the first 5 terms just for kicks. Let's do one more, sorry. So this would be when n equals 4. Negative. So if n is 4, the top is 4, right? The bottom would be -7, right? So -4/7. Okay, so this is just a sequence here, and all I'm doing is listing out this listing of numbers in the sequence, right? And you can try to decipher a number of things to this, for this. You know, clearly we start at 0, we drop down to -1, but then doesn't it seem like we're heading back towards 0? Maybe? So there'd be some interesting things we could decipher for this, but we're going to We're going to kind of keep moving through this. I just want to make sure you knew what a sequence was. We're going to mostly focus on series here, but I do want to talk about the limit of a sequence, and you guys are going to want your calculators for this. And so grab your calculators. We're just going to jump up to here. Grab your calculators. We'll do one or two of these. Yeah, this will work time-wise. So take a look at that first one right there. It's 3 plus negative 1 to the n. And you guys finally, it's crazy. I like to think about where you've been. Like up to this year, I think you guys were mostly in rectangular mode on your calculators. You might have done a little bit of polar mode in pre-calc. You'd never done parametric. We did that. And we're actually going to use the final mode here. So push mode. And you guys see, if you go down there, you got function, parametric, polar, and then SEQ. Sequence. So slide over there to sequence. We're going to use your calculator to kind of help you see sequences a little bit. You guys all in sequence mode? Okay. So go to y equals, and it's going to look a little funky. Yeah. So notice what it gives you. It says n min. So this is asking essentially, what do you want the low start value to be? So we used zeros a lot for our min with our sigmas just a second ago. This one's starting at 1. You can make that really whatever you want. And then it has u of n, right? So u of n is going to be the function that generates the terms in the sequence. And so we have 3 plus negative 1 to the n. So let's type that in. 3 plus parentheses negative 1 to the n. Oops. I got to put a little exponent in there to the n. There we go. So we're going to start at 1, and so you can do these terms in your head quite easily, right? So if you plug in a 1, you get 3 plus negative 1, which is 2. You plug in a 2 for n, you get 3 plus 1, which is 4. Let's see what this looks like on a graph. So this should go zoom 6, I guess, on the graph. You guys get something like that? So what you can see here is the x-coordinates are going to be your n's. So when n is 1, the sequence value is 2. When n is 2, the sequence value is 4. And you basically see the sequence just goes 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4. So this is an example of a sequence that, if you think about the limit of this sequence as the number of terms goes to infinity, this sequence does not really converge to any one particular term, right? It just goes 2, 4, 2, 4, 2, 4, 2, 4. So if you said, well, where is the sequence headed? You'd have to say, it's not really headed anywhere, right? It's just oscillating between 2 and 4 constantly. So we can't say that it really converges towards any one particular number. So if you take a look at a different one, the next one you guys have, let's do number 2. Let's change this. We'll go away from this one that just oscillates back and forth between 2 and 4. I'm going to clear this out. And this one is a fraction. So this is n squared over 2 to the n minus 1. And I'd like for you guys, as you think about this one, think about the rankings thing we talked about yesterday. Please, no soundtrack needed. Lenny, don't make me treat you like an Algebra 1 student and make you put your phone away. Yes. So anyways, think about your rankings thing. What class of function is in the numerator?
X to the n. Exponential.
No, the numerator is not an exponential.
Whatever it's called.
Oh.
Polynomial, right? And the denominator's got that minus 1 in there, but what's like the dominating feature of the denominator?
Exponential.
It's exponential. And so when you think about long-term behavior, as n gets super duper huge, what would you predict this would do?
Zero.
Head towards 0, yeah. So as you look at the graph here, if I go zoom 6, I don't know if I'll see all that I want to see. No, actually that's pretty darn good, right? You can see that it kind of goes up a little bit, and that's the part where that first little part is where the numerator for just a brief time overpowers the denominator, but then very quickly the denominator starts to dominate and we start heading towards 0. And so you look at this, you could look at the terms here, you could look at a table. I don't know where my table's at. No, I don't want that. Let's go table set at 1. And how about 1? So when you look at your table,
You did good.
you can see what these terms are doing, right? The first one is 1, then it's 1.33, and that's where we start to drop down a little bit. If I were to just ask you, based on the graph and based on the table, to venture a guess, what do you think the limit of this sequence would be? What would you say?
0?
0. Yeah, so this actually does converge to a particular value, or at least we think it does at this point. Graphically it appears so. We'll investigate that further as we move forward. This makes sense? We're talking about sequences right now. Any questions? Okay, you guys are doing really well, I think. Let me get back on track here. We're not going to do anything with 3. I want to get into this right now. So let's just do a little note right here. We'll go back up. Notice this note. It says the convergence and divergence of a series, that should say of, not or, of a series is different than for a sequence. And the reason is what Caroline said, right? So a sequence is just a listing out of the numbers. This one, then this one, dot, dot, dot. A series is we're going to take all those terms and we're going to go and add them up. This plus this plus this plus this. And so this makes a difference. And you know what? Let me illustrate this right here. Let me illustrate why this is different. If we'll get into this with some partial sums, but I want to use a graph since we were just doing the calculator. If, listen up then. Let's say, I'm just going to say this is 5. Let's say we graphed the terms of a sequence, and let's say the first term was here, or the 0th term was there, maybe the first term, second term, third term, fourth term, fifth term, so on and so forth. We're just building this way out here. If I were to say, hey, those are the terms of a sequence, right? We graphed it or whatever, and I said, does this sequence appear to converge to any one particular number? What would you say? Doesn't it appear that, I mean, based on my admittedly mediocre graph, doesn't it look like we're converging towards 5? Okay, so if I were to say, does the sequence converge, you would have to say, based on my graph, you'd have to say yes. I mean, it's not the greatest evidence in the world, but based on the evidence you got, you'd have to say yes. If, however, I asked a different question, and that question was, does the series converge? Based on what Caroline said, and we all have recognized that a series is basically taking all those numbers in sequence and adding them, would you say that this series would converge to a real number? I'm asking you to make a little bit of a leap here. We'll go back and start looking at partial sums. But what do you think? Why not? The answer would definitely be no. Yeah, as you get closer and closer to having an infinite number of terms, wouldn't you essentially at the end just be going plus 5, plus 5, plus 5, plus 5, plus 5? Or like plus slightly bigger than 5, then not quite as big as that, but still almost 5. You'd just be essentially adding 5 over and over and over and over again. And since we're looking for an infinite number of terms, if you add 5 forever, you're not going to be converging to a real number. You're going to be heading towards what? Infinity, right? So, in other words, a non-existent answer. Let me show you a little contrast here. Oh, I didn't want to do that. Let me do this. What if I had a different sequence, and let's say this sequence did this. Let's say that this was my 0th term. There's my 1 term, 2, 3, 4, 5, 6, 7, 8, so on and so forth, like that. If I asked you the same 2 questions, there's my terms in my sequence, graphed it again. Would you guys say that that sequence converges? Yes or no? Based on my graph. What would you say that my sequence converges towards?
0.
I'm trying to make it look like 0. So I think we could say for sure the sequence does converge, and it looks like it's converging towards 0. So let's assume that that's what the case is. So then, if we were to say, all right, let's ask the other question, does the series converge? What would you say to this? You want to know the real answer?
No. I mean, it's no.
All right, that'll be all for me. No. You want to know the answer is? The answer is maybe.
Oh, really? You're kidding.
Maybe. A lot of times the answer will be yes. A lot of times the answer will be yes. In certain cases, the answer will be actually no. We're going to investigate that a little bit here in a second. Okay? So if the terms in the series are heading towards 0, then it possibly will be a converging series. But in some cases, not. We did talk about this a little bit when we talked about improper integrals, right? Remember how we said, does it get there fast enough? Fast enough? That's where we're going to start talking about things like that. You're right. Okay, so let's do couple of partial sums here, kind of get a sense of what's going on. And so a partial sum is essentially this. What if you had a series, and it's an infinite series? So if you look at what we've got right here, clearly because of that upper element on the sigma, it's an infinite series, right? It just goes on and on forever. Believe it or not, it's really hard to find out what they add up to be. It's really difficult. Very smart mathematicians spend many, many years proving that, yes, in fact, this does add up to be such and such a number. Not as easy as we would hope. But what we can do is we can do what's called partial sums. And partial sums are essentially, well, we really don't feel like adding up an infinite number of them. Why don't we just add up like 3 or 5 or 7 of them or something like that, and use that to kind of estimate or predict what's going on. So let me do S3 for you. S3 would basically be when n is 3. So if n is 1, my first term, so I'm going to say S3 equals, if n is 1, my first term would be 1/2. And since this is a sigma, this is a series, we're adding everything up. So I started at 1. My next n value is 2. So that would be plus 1/4 because 2 squared is 4. And then when n is 3, that's where I'm going to stop here. 2 cubed is 8. So it'd be 1/2 plus 1/4 plus 1/8. So 4/8 plus 2/8 is 6/8 plus 1/8 is 7/8. So if you had to just take a stab at this right now, I mean, this is admittedly pretty meager evidence. If you had to take a stab at this, what would you bet we're headed towards as far as an actual sum? Okay, let's see if some more evidence supports that. Let's see if you guys can find S5. So S5 would basically just be a continuation of what you just did. So if I were you, I would say S5 is 7/8 plus 2 more terms instead of relisting them all out. Feel free to list them all out if you feel like it.
I was supposed to meet with Donna.
Let's see here. What is it? When you plug in a 4, don't you guys get 1/16? Then you plug in a 5, you get 1/32. So what is this? 28, 30. You get 31 32nds?
Yep.
Okay. So you guys, threw it out there. It looks like we're heading towards 1. Isn't this a little more convincing evidence now? You could say, hey, yeah, we're getting closer to 1, because before we were 1/8 away from 1. Now we're 1/32 away from 1. And I don't know if you guys have done S7 or not yet, but I bet you'd be 1/128 away from 1, right? And so that's obviously the distance from our sum to 1 is just getting smaller and smaller and smaller. And so just from a anecdotal perspective, you could say, yeah, I think we're probably heading towards 1. We can actually prove this quite well. We will later. So does this series seem to converge or diverge? I would say the series is definitely converging. And if we wanted to be specific, it looks like it's converging to 1. We don't have great evidence yet, but we have some, circumstantial evidence for sure that maybe it's heading towards 1. Does that make sense? Okay, so the next one, please forgive me, the next one is just a tad ridiculous. Sigma from 1 to infinity, and your nth term is n. So obviously this is for point of illustration.
Infinity.
Yeah, well, let's check this out. It might not be obvious at first, but we're going to look at a pattern. S2 would be 1 plus 2. Of course, that's 3. And then if n is 4, it would be 3 plus 3 plus 4. So now we're at 10. S6 would be 10 plus 5 plus 6. So how about 21? So you can see the pattern is going on here where, these partial sums are not really heading anywhere towards any one particular number, right? They're just getting bigger and bigger and bigger. And you can see like, hey, what if we did S1000? Be a huge number, right? And so as we look at something like this and we ask the question, does this look like this series is converging or diverging? We would say it's diverging. Diverging is another way of saying the sum doesn't exist, right? So we'd say diverging, also code word for we're heading towards infinity, right? It's not a real number, it doesn't exist, and so we usually say that this series diverges in those cases. But again, our evidence is pretty thin. All we did is we added up some numbers and said, I see a pattern. Right? That's not necessarily going to hold up that great under close examination. We're just trying to get a sense of what's kind of the mechanics of it. We good? We're going to start proving this for real, I think, right now. If I remember right, yes. Okay. So I have a note up there. If you were going to try to do all the stuff we're going to do here by computing a bunch of partial sums, like your head's going to explode at some point just from like the sheer magnitude of trying to compute like tens of thousands of terms potentially, just trying to figure out what the pattern is. And so we're going to start using some tests to kind of help us narrow things down. And so I think so, at least this one of these first ones, geometric series, you guys have seen in pre-calc. And so I want to give you like a little bit of a narrative to help you understand. Just to kind of personalize it a little bit, here's the way that I approach this. I think of like these series, because basically, let me just boil it down to this. For most of these series, the question is going to be, does it converge, does it diverge, and why? Right? So those are going to be kind of the choices that we make. And so I kind of like to think of us as being, I don't know, like mom and dad in the stands at the game, and we're like cheering for someone. Like if you're cheering for your kid, you're cheering for your kid to be successful, right? Even if they look bad, they look like they haven't been practicing, you're still like, come on, you can do it, right? You're like super enthusiastic. You want them to do well because it's your kid and you love them, right? I would hope that if you were a parent, you would feel that way. Anyways, you haven't been a parent yet, so you don't know, but you probably will. Anyway, so I like to think of us as like cheering for these series to converge. Like, you can do it, little series. Come on, you can do it. I know you can converge to a real number. You don't have to be one of those. Come on, McKenna.
That's where I draw the line.
Put on your future mom hat. Come on, come on. We're going to keep pushing. We're going to keep pushing on you. No. That's way over the line. Anyways, so if you can suspend your disbelief for just a few minutes, McKenna, please do. We're going to be cheering for these series to converge. Some of them are just going to make bad choices and they're going to diverge, and we can't really help that. But we are going to be cheering for them to converge. There are going to be some obstacles along the way. Listen, just like in a game, a team or whatever, there's going to be an occasional referee or maybe a coach that's like very negative, right? That the only thing they will really tell you. Have you ever had one of those coaches where, you know, you work really hard and you try really hard and you're successful and the response is, essentially, that's what I expected. Like, no, really, listen, have you ever had a coach where you do great and you succeed and the response is basically silence because that's just kind of what they expected? But as soon as you mess up, it's like, oh, come on, you know, they get really upset with you. That's like a really negative way of coaching. And for some people that works, but for most people that doesn't work that well. And so there's going to be some of those people along the way that the only thing they're going to do is like be super negative and mean. There are going to be other people that are going to be, you know who I'm talking about when I say like the soccer mom? That she's the one that brings like the sugar cookies, the lemonade and all that stuff. And the only thing she has really to say is positive stuff. Hey, have a great day. It was nice to meet you.
Good luck on BC, guys.
They don't need it. They're awesome.
They're awesome.
So anyways, you know the soccer mom where even if you objectively you just played like the worst game of your life. Listen. You know the soccer mom, you just played like a terrible game and you know it, but she's like, "Oh, great job. You tried so hard out there." Like or maybe it's a soccer dad or something. All they can really say is positive stuff. There's going to be some of those people too. And there's going to be other people that are really balanced. And they're going to be like, well, you know what? If you stink, they're going to be like, that was pretty bad. We need to get better. And if you were great, they're going to be like, that was awesome. Keep it up, right? They're going to be very balanced. And so we're going to like navigate these different tests. And some of them are going to be nice. Some of them are going to be mean. Some of them are going to be pretty balanced. We just got to learn to navigate through those. Does that make sense?
Yeah.
When I say these various people, I'm talking about the tests that our series have to go through. Make sense? We're going to personalize this a little bit. I don't know. I think it's fun. McKenna doesn't think it's fun yet, but that's okay. So we are going to, for our first effort, we are going to look at probably the most negative coach or referee or whatever that you're going to come across, and that is the nth term test. Okay? So I know. They don't get much out of their players, but whatever. They're still there. So the nth term test basically is only going to say one thing. It's going to either say, series, you diverge. But if the series is bound to converge, like if we find out later the series is going to converge, the nth term test is going to say nothing. Right? So this is that coach I talked about where if you do something great, just don't say anything. But if you do something terrible, they're going to call you on it and say that was bad. That makes sense? So the nth term test effectively only says one thing. It says you diverge. And if the nth term test is silent, we got to move on to something else. Make sense? Okay, so here it is. The nth term test is if the limit is n goes to infinity, and this right here, this a sub n stands for the nth term. So this would be like that general term that we were working on with those sigmas, right? So if you do the limit of the terms, right, you say as n goes to infinity, where are the terms headed? If that number is anything other than 0, then the series diverges. And this is that example that we talked about a second ago with the 5s, right? So if the sequence heads towards 5, then the nth term would be heading towards 5, and that's not 0, so you'd get a divergent series, right? So if you go limit as n goes to infinity of the nth term, and you get anything other than 0, the nth term test will be like, it diverges. But if you do get 0, this is that maybe. Remember what I said before with that little sequence map? If you do this limit as n goes to infinity and you get 0, the answer is, keep going. Maybe you converge, maybe you don't. But this guy at least didn't stop you. I put this in here. The inverse of this test is not necessarily true. This is probably the number one pitfall for students that are first learning about series. They'll go limit as n goes to infinity and they get 0 and they're like, yes, it converges, yay, and you clap and cheer. Maybe not. There's going to be some cases where that is not true. It just means you keep going. You don't stop right there. And then there's also the geometric series test. The geometric series, I'm definitely relying on the idea that you saw this in pre-calc. Geometric series is basically a series in which the next term is found by multiplying the previous term by a common ratio, and you get the next one by multiplying by another common ratio. Just keep multiplying to get the next term over and over and over again. So the geometric series with a common ratio of r diverges if the absolute value of r is bigger than or equal to 1. But if the absolute value of r is between 0 and 1, in other words, a fraction, right? Then you're going to get a converging series. So really what you have to look at there is you have to identify what is the common ratio. If you can identify that, you can run it through this test and you can tell. So I would say the nth term test is like the super negative coach or person that only tells you when you do bad stuff. The geometric series test, be more balanced. It'll say, well, hey, you know what? You did a great job. You converge. Not so good. You're diverging. It'll tell you both ways. So geometric series test, pretty balanced. And then one thing that's unique about the geometric series is that this is really, honestly, this is the only series in which we're actually going to be able to find the sum. So with geometric series, you can say, yes, this series converges. And as a matter of fact, the answer would be whatever. You could actually give a numerical answer to this. Could be 4. Could be 1. Could be just about anything. Most of the other series, pretty much all the other series, we're just going to be able to say it converges or diverges, but we won't be able to say and it equals whatever. Okay, so you guys have 2 tests with which to use here, the nth term test and the geometric series test. And we got a few minutes to investigate. And so let's try some of these, starting with number 1. So let me get this set. Come on. So this is going to be, there's going to be a little bit of lack of comfort here. Perhaps, maybe not. Hopefully you're really comfortable. But there might be some moments where you're just like, oh my gosh, I don't even know where to start sometimes. And we can kind of work through that and help you. I just want to give you a chance. There's only 2 possibilities here, right? You can use either and or the nth term test, the geometric series test. Some of these cases, both of them will work. Other cases, it won't work. No, I would say 99.9% of these will be a no calculator proposition. So I'd say at this stage, let's not. So just look at number 1. I'll give you an example of what this could have looked like. I think you could have taken either of the 2 routes. I think both would work here. Here is one option. You could have said, you know what, I'm going to try out the nth term test. In fact, we are going to talk about the nth term test as probably being your gateway into all the other tests. I really think you, at the very least, you need to do a mental nth term test on all the series we do. You're going to, I think, eventually find that to be pretty easy based on the rankings thing that we do. But I think you want to do that first because if like I said, that's the negative one. So if a series does not converge based on the nth term test, you're just done. So it'd be unwise to ignore that. So I'm going to start with that. So I'm going to say limit as n goes to infinity of 2 to the n. And I need to stop and think for a second, okay, what's the pattern here? What's going to happen if I go 2 to the n is heading towards infinity and I'm going to be adding up all these terms? So it'd be like say 2 to the first plus 2 to the 2 plus 2 to the 3. The important thing to ask here is this sum heading towards, or is this nth term heading towards 0?
No.
Oh man, it's definitely not. So all you really have to put here is this sum, or this nth term, excuse me, is not heading towards 0. It's actually getting bigger and bigger and bigger as we move n towards infinity, right? And so that is not 0. And so what we can do right here is we can stop and we can say, therefore, because of the nth term test, the series diverges, would be the right way to say that. So diverges is the correct answer, but you need to have your limit expression and name the nth term test for me, explaining like what it is that you use, make that connection between the terminology and the mechanics of it. Did any of you guys use the geometric series? You really could have. What's the common ratio?
Well, A is 1, R is 2, so.
Yeah, common ratio is 2. Common ratio is 2, yeah. So yeah, you could have done that as well. So you could have said, for this is a geometric series. And like you said, Darian, R is 2, right? Because to get the next term, you're just going to multiply by 2, and then 2, and then 2, and then 2. So R is 2, and because the absolute value of R is 2, and that is bigger than or equal to 1, therefore, so you'd say something like this, therefore, because of, you can abbreviate these, you can say because of the GST, geometric series test, the series diverges. So you really could have proved it either way. I want to make sure you understand, I'm quite sure you do, but just to make sure. Geometric series, of course, is characterized by a numerical base and a variable exponent, right? So if you see a numerical base with a variable exponent, that's a key mark of a geometric series element. Is that good? So, I know you know that there's more coming, but so far so good with series? So far so good? Okay. Why don't you guys take a look at number 2?
And the first one is A.
So number 2 is sigma from 0 to infinity of 2 to the n over 5 to the n plus 2. I think there's like a smidge, a little bit of algebra that you'd want to do here.
I know, but I'm like having.
I'm starting to hear some good stuff coming from over there. Yes, sir.
To do the geometric series test, would you recommend just saying getting the first term and then finding what you would need to multiply it by?
So first term is potentially helpful, but the R is the more helpful thing.
Right,
If you can
so-
figure out the R, you can jump right to.
I'm saying like, what's the best way of getting R?
So yeah, good. So Caleb was asking, what is the most efficient way of figuring out what R is? Can you guys see that this involves some geometric elements, right? Clearly, you've got a numerical base with a variable exponent, and so we'll talk about the nth term test a little bit. But because it's pretty clearly geometric, maybe we think about that, right? So here would be some stuff I would do before I got going too far. I would want to recognize that the top is 2 to the n, and the bottom, we're adding exponents, right? We talked about this the other day. If you're adding exponents, what are you really doing with the bases? You're really multiplying them, yeah. So this is, the denominator is really 5 to the n times 5 squared. So I'd do a little bit of algebra. I'd keep going with this. Notice that the sigma only applies to anything that has an n on it. And so what I could then do is I could get that 5 squared out of there, and I could rewrite it as 1/25 sigma from 0 to infinity. And then it would be 2 to the n over 5 to the n. This is cleaned up significantly, but I still can see how someone wouldn't be able to see the common ratio. The last thing that I would do to help see that, and this will get finally around to Caleb's question, and that is, I hate to say this, but it goes back to Algebra 1 exponent properties. If you've got a fraction in which the numerator has an exponent and the denominator has the same exponent, you can rewrite it like this.
That's exciting.
So 2 to the n over 5 to the n is the exact same thing as 2/5 to the n. And that's what I thought I heard you say, McKenna, right? You're like, it's just 2/5, right? So I would go this route if I were you. You could do the nth term test. It's not going to be maybe as clear as it was on the previous one. Since the geometric series test is balanced and tells you both aspects, then I would probably use that for this one. So. So that Mr. Whitlow is a teaching candidate for next year potentially. So. Yeah, he taught Mr. Scott's honors algebra 2. It's usually just a scheduling thing. It's like, where does the schedule all work out? So it's not necessarily a particular class, but yeah, so he's just kind of taking the tour and just visiting various classrooms and things like that. So, anyway. All right, so Caleb, did this clear up the R?
Yeah.
Okay, so R is equal to 2/5. And, you know, if we're going to figure out the full sum, the 1/25 is important for sure. But since we're only looking for convergence or divergence, it's not that important. We'd say R is equal to 2/5, and that means the absolute value of R is equal to 2/5. That is less than 1. The absolute value of that is less than 1. Therefore, by the GST, the series converges. So we will get a mix. There will be some series that converge, and we say, yay, good job, series. Other series will diverge, and we'll be sad with the series. Caroline.
So yeah, if we were to find where it converges.
Can we do that?
Yeah.
Let's do that real quick. So this did not ask what the actual sum was, but we can figure that out. So that formula for the sum of a geometric series is first term over 1 minus r. And so we got to do just some quick mental math here to figure a couple of these things out. So I'm going to focus on this right here to help me with this sum. So if n is 0, then my first term would be 2/5 to the 0, which is 1 times 1/25. So I would say my first term is 1/25. So for the full sum, it would be 1/25 over 1 minus the common ratio. The common ratio we already used, we know, is 2/5. So this would be 1/25 over 3/5. So that is 1/25. Sorry, it's getting a little messy here. Times 5/3. Oh, it went off the edge. So how about 1/15? Make sense? That would be the actual sum that this series converges to. And just to be clear, Caroline, on your question, you don't have to do that unless it says, what is the sum? Or if it said, evaluate, or something like that, then you do have to go all the way to that. But a hint, that you'll only be asked to do that with the geometric series, because that's the one that we actually are equipped with, something we can use relatively quickly. Okay, take a look at number 3. This might be where we finish. We shall see. I don't know. There we go. How about 3? Trig, you're right. Trig is not awful. Trig is beautiful.
I'm friends with it now.
But it's
She was
not
just, like,
easy.
her first day, and she was like, this is...
She needs to have a little more open mind, right?
Yeah.
Just like let it simmer for a bit and you'll be all right. Hey, so a question for you guys. Did you get the 3 out of there? The 3 is potentially a really confusing thing, but since it doesn't have an n directly attached to it, the sigma doesn't really have any effect on it. So if you do that, you get this. And again, I want to point out the significance of this. You basically, what you have here is a numerical base with a variable exponent, right? So that means that just screams geometric, right? Numerical base, variable exponent. There's got to be some geometric element to it. But finding the common ratio could be a little bit tough. What did you guys think the common ratio was?
1/2.
It's 1/2, yep. So it'd be 3 sigma n equals 0 to infinity. Oops, that's an infinity. You could write it as 1/2 to the n. So then since your common ratio, the absolute value of your common ratio is 1/2, that number is less than 1. Yeah, sorry. Let me write that a little bit better. I don't want that just to be less than 1. I want the common ratio to be between 0 and 1. There we go. Therefore, because of the GST, the series converges. Okay. We got a couple more of these we'll try. We got a kind of a cool bouncy ball problem we'll do next time. And then we'll get into a couple of other series tests. And that'll be for Monday, of course. Tomorrow is your test over